So Vincenzo closed the first part by telling you about how currently the experimental setup of continual learning experiments is very limited. So I want to show you now what you can do to improve on it, because there are many solutions in the literature right now. They are just not that popular. First, I'm going to talk to you about benchmarks that you can use, then about metrics and evaluation, and finally, I will discuss a little bit about open questions in distributed continual learning. So for the realistic streams, we're going to see what are the properties that matter for a continual learning benchmark. We're going to talk about real drifts and streaming data, and then how to use simulators and synthetic data generators. This is a picture taken from CLAD, which is a continual learning benchmark for autonomous driving. You can see on one axis the type of drift, so whether it's class incremental, domain incremental, or a bit of both, and whether you have sharp drifts or gradual drifts. And what you see is that most of the papers are focused here, the class incremental setup. But the reality is that real world data doesn't look like that, but it's going to be somewhere here in the middle. We have some benchmarks, but the area of the circle is the number of times that benchmark has been cited in a paper. You can see they are not used very much. So what are the properties that we would like to have in a realistic benchmark? And we compare this with the popular class incremental setup. So we want gradual and sharp drifts, while class incremental has only sharp drifts. There are some experiments with gradual drifts. We want both new domain and classes to appear over time, while we have only new classes in class incremental. We want repetitions, like repetition of all domains and classes are a natural properties of a stream, while in class incremental, we don't have repetition. If you think about it, if you don't have repetition, you don't really need to remember the old data, because if you don't see it again, you don't really care about it. We have imbalanced distributions, while class incremental, the dataset that we use are almost always balanced. We want real drift. I mean, this depends on the application, but many times you have real drift, so the objective function, like the boundary between classes, is changing, while in class incremental, it doesn't. And another property is temporal consistency. So if you have, I don't know, a camera in a car, then you have frames from the video. These frames are going to be temporally consistent, while class incremental streams are not. And of course, all of these properties have an impact then on how you design the methods. So for example, many methods have different components for different tasks and domains. But then if you don't know when you are switching to a new task, it's difficult to freeze all the units, or you would have to do task and domain inference, which is also more difficult if you have many batches with many different domains and tasks. Same for the labels. In some way, classes, if your drifts are determined by classes, then you implicitly have some kind of labels for the drift, because you know when you see a new class, there is something new. Instead, new domains usually don't come with a label. Same for repetitions. Like if you have some methods like progressive neural network, task incremental methods that freeze old components, but then if you encounter the data for the old task again, then you cannot change it anymore. You can change the old component anymore. Of course, we don't want to do this. For imbalance, for example, think about reservoir sampling. So the replay method that randomly samples from the stream is a very strong baseline when you have balanced data, but it actually doesn't work if you have unbalanced data, because your replay buffer is going to be unbalanced too, and you want to avoid that. And same for real drift. If you have real drift, the data that you store in your replay buffer maybe is wrong right now, so you are going to rehearse knowledge that is wrong. So how does it work when you want to evaluate on benchmarks with real drift. So in virtual drift, what you do, let's say that you have data split by here. You keep this a small part of your data as a test set, like you can see here, and you evaluate on all the batches for each here, because you know that the old data is still relevant. When you have real drift, like here I put the example of politician roles and affiliations because it's something that is changing very quickly in Italy. You don't care about what happened in the past because it's not relevant anymore. I mean, it may what happened in the past and what the model learned in the past may be useful to learn something new, but it's not important to remember how to predict it, right? So we do what is called frequential evaluation. In frequential evaluation, basically, whenever you get some data, first you test on it, and then you use it for training. Like here, so you test on 2005, and then you train on it. Then you test on 2006, and you train on it. And every time, like you only train on the new data, which is actually what a real application on a stream will do. Like you have a single stream, you don't have a parallel train and test stream, and you always predict on the data, then maybe label some of it, and use it for training. To give you an example of how much of a difference there is between frequential evaluation and the normal one, think about data ordered by class. So you have all the zeros before, and then all the ones, one sample at a time. So the persistent classifier is the naive baseline that just predicts the previous class. So here, you are going to say 0 because the previous sample is a 0. And this baseline is optimal because you are exploiting the fact that all the zeros and all the ones are clustered together. So you are exploiting the temporal consistency. And it's actually an information that you want to exploit. Like maybe you are in a domain where you only see the zeros, then it's good that your model is able to exploit this fact. There are some benchmarks that you can use to test in a scenario with real drift. Like these are examples of image classification, so clear and wild time. You have images basically that are tagged with the timestamp of the image, so you can order them by time and use the frequential evaluation to test on it. Another interesting property of clear is that it's semi-supervised, so you have a small amount of labeled data and a larger amount of unlabeled data. And again, this is something that is you will find in a real application. If you have a lot of data and you need to label it explicitly, probably you don't want to label all the data. Same for wild time. Wild time is actually 5 data sets. There are images, but there are also biomedical data, satellite data, like the archive abstract, and so on. Another one is clock. So this is the continual localization paper. They have the nice thing about this is that it's very large, 39 million images. But even though it's very large, continual learning experiments are quite fast. For example, the paper that used this benchmark do online continual learning. So they do just a few passes for each sample. So it's relatively quick to test. It's a localization task, so you have to guess the region of the image, basically. You can see in the plot here that like the green curve is the paper trend on 2010, and it's good for data from that year, but it's not good for data before and after. So this is telling you that there is real drift, and this drift has an impact on the accuracy. Like sometimes you can have real drift, which doesn't really change the accuracy. So for temporal coherence, a good benchmark can be Core 50. So Core 50 is a collection of videos of manipulation of an object. So imagine that you have a continual learning on the edge application where you have a pre-trained model that is already trained to recognize a certain number of objects, and you want to add a new class. So what you do is that you take your smartphone, you do a short video of the object to do your data collection, and then you fine-tune the model with this new set of samples, right? So Core 50 is exactly this kind of application. And the nice thing is that there are several different scenarios defined for the different settings that you can have. So whether you want the coherent videos or whether you want all the videos of a particular object but shuffled to make it a little bit easier for the model, and so on. So finally, another interesting kind of benchmarks are simulators and synthetic data. So for simulators, you can take a look at this paper that is basically a procedural simulator based on the Unreal Engine, I think. And it allows you to choose how and when new classes appear. It allows you to change the weather, to change the illumination, and so on. There is, again, temporal consistency because it's a camera on a car. So it's going to see what the car is seeing. And you can do the same for supervised data with static data sets. So this is a paper from us that we actually published at CoLLAs. The idea is to do the same thing that we do with class-incremental learning scenarios, but make it a little bit more flexible. So you start from a static data set. You define some parameters of the distribution, like the length of the stream that you want, the probability of each class, so you can make them unbalanced, or how many repetitions you want to have. So you get probabilistic definition of your stream that is, again, a bit more complex than the normal class incremental setup. And you can sample a stream from it, and then you can train on it. And these parameters can be used to tweak the difficulty of the stream. There is a poster session today, so if you want to know more, you can also come at the poster. So one of the things that we try to do with this kind of synthetic generator is to make a much longer stream than what is used in the literature. So and with a small amount of repetitions. So this is not equivalent to replay, because with repetitions, every time you see some classes that are old, but you don't see all of them, and you don't see the same examples every time. So what you can see here is that the naive baseline, so the one without replay, is approaching over time the accuracy of the naive of the replay baseline. So of course, the replay baseline is faster to converge, but overall, the gap between the two is getting smaller and smaller over time. So natural repetition, in some sense, diminish the effect of continual, I mean, diminish the motivation for using replay. So if we look at what's happening to missing classes, like here we have the accuracy for a single class. The blue dots are when the class is present, while the orange dots are when the class is missing. And you can see that at first, the accuracy drops to 0 whenever the class is not seen in the stream. But then over time, the model is becoming more stable. So it doesn't forget completely, but it's starting to remember more and more. And this is, again, naive fine-tuning. So if you use a smarter continual learning method, of course, this effect is going to be even better. And again, another thing that must be pointed out is that these are long stream. So if you use the class incremental setup, you are going to end up with like maybe 100 experiences if you see one class at a time. While this is 500, so it's much longer. And here on the right, instead, is the unbalanced stream. So again, as I said before, green curve is reservoir sampling, so random samples from the stream. And of course, if you use random samples in an unbalanced stream, your replay buffer is going to be unbalanced. And instead, if you try to do something that is inversely proportional to the frequency, then it goes much better because it counteracts the imbalance of the real stream. OK, so just to recap this first part, there are some properties that we care a lot about continual learning streams that are missing right now in the experimental settings that are popular, which are gradual drift. Gradual drift is something that is more studied than the other. New domains and classes at the same time, the concept of repetitions, like it would happen in a natural stream, temporal coherence, like you get from videos, and real drift, where the concepts, so the boundaries between classes, are really changing. The good news is that there are benchmarks that you can use to test these kind of things. So you don't have to invent something completely new, like while time, clear, and clock. And you can use the frequential evaluation to check how the model behaves. So when you use the frequential evaluation, the objective becomes more like fast adaptation to new data than not forgetting what you have seen before. You have streaming data like Core 50 and simulators and synthetic generator to control in a more careful way how you generate the stream, and also to control that a method is robust to different parameters of the streams. OK, so now we start talking about metrics and evaluation in online continual learning. I'm going to use a paper that we recently published that is like an empirical evaluation of online continual learning methods, just for convenience so that I can show you an example end-to-end. So first, I want to talk about the metrics that we can use for online continual learning, some results that we get that give an overview of the current performance of popular method in online continual learning. And finally, I want to talk a little bit about robustness to hyperparameter choices, which is a bit of a problem in continual learning. So first of all, what is online continual learning? We have two properties that define online continual learning, and two properties that we would really like online continual learning methods to have, but they are not mandatory. So first, it's online, so data arrives in small mini batches. Usually, when people say online, they mean one sample at a time, but we have deep learning methods, so we imagine that we wait until we have enough samples, and then we send a mini batch. Possibly, they come from a real stream, so you have a real-time constraint, like you cannot stop the stream until the model is trained on the new data. And real-time constraints are not studied that much, but there is still the idea that you have strong constraint, both in terms of memory and computational budget. Of course, the exact constraint depends on the application, but the general idea is that. The second property is the property of anytime inference. So if you have an online model, you want to be able to predict using that model at any point in time, so even during a drift. This means that during training, there must not be a moment where the model is not good and it will have bad accuracy. And then we have desiderata. First, we want methods that are task agnostic often, so they don't need task labels to know to discriminate between the different tasks. We just have one large task where that must be solved. And then the property of being boundary agnostic, so the methods should not assume knowledge about when the drift happens. So this is called task-free in the literature. In general, many methods are not boundary agnostic. And this is, I think, another of the weak points of the class incremental setup, because in the class incremental setup, you know when there is a boundary because you see a new class that is unseen, and you can do something to, let's say, prepare the model for the new class. Then, which means, of course, you know when the drift happened. I'm going to focus on replay-based methods. So in online continual learning, replay methods have more or less this algorithm. So first, they receive this new mini batch, x new, y new. This is not controlled by the method, of course. It's the training stream, so something that is given. You cannot choose the order or anything. And then for each sample, they do a certain number of training passes. And for each pass, the sample usually is going to be augmented because this works very well and improve the performance. Then you sample from the replay memory and augment again. And finally, you do the classic backpropagation stuff. So you compute the loss, backpropagate, and update the weight. At the end, after training, you update the memory. So you decide whether you want to add some samples from your current mini batch to the memory and remove some of the old ones. And then you do the evaluation. In a frequential evaluation setting, the evaluation is actually here on top. So you will do the evaluation of x new, y new, and then you will do the training on it. Most continual learning methods in the online setting fit this high-level schema. They just change one or more of the operations. Like you have methods like rar and mir that either find the best sample to use for replay or use adversarial augmentation to create samples. Methods like AGEM that use the memory but only for gradient projection. Many methods that are changing the loss function to be more robust to the introduction of new classes. And some methods that change the classifier for evaluation, like SCR, use the nearest class mean at inference time. So this is the general idea of replay-based methods. So how do we evaluate these methods in an online continual learning setting? I'm going to focus on 3 different properties. First, knowledge accumulation. So the idea that the model should improve over time. And I talked before about anytime inference. So the model must be able to predict at any point in time. So we want the model to be good during the entire training. And this means both high average accuracy, very little forgetting, and fast adaptation. We want stability, so the fact that the model should not forget any previous knowledge, again, at any point in time. And keep in mind, when we measure stability, forgetting, we measure this on the old task, on the old data. So we often assume virtual drift. We assume that the things that we have seen before are still relevant right now. And finally, the representation quality. So sometimes it can be useful to check how the latent representation perform, like with linear probing. This is, you can see it as a weaker form of knowledge accumulation and stability. And the nice thing is that you can also evaluate this on out-of-distribution data that the model has never seen, or for self-supervised models. And it's important also because sometimes the representation, even when there is a very high forgetting, the representation are good. It's just that the classifier is misaligned because of training on the new data. OK, so how do we measure knowledge accumulation? We can just take the average anytime accuracy, so the accuracy along the entire curve. Like the curve here that I use in this and the next slide is basically the accuracy on a single task, this orange curve, where the red diamonds are the task boundaries. So when in a class incremental setting is when the new classes are introduced, right? So to measure knowledge accumulation, accuracy along the entire curve. This is different from what is used in many papers. Actually, sometimes you see the average accuracy at the end of training. So that will be the final diamond, or the average at task boundaries, which will be the average of task diamonds. Again, very different results. You can see that if you compute the average of the diamonds, you are going to get something that is quite different from the average along the curves. Then for getting, one thing that I want to mention is that forgetting is actually quite tricky in the original definition, at least in the class incremental, in the single task setting, because it's measuring two things. It's measuring how much the model has forgot about the old task, but it's also measuring that the fact that the task is becoming harder and harder over time. So if you measure, let's say at first you have 10 classes and you have a certain accuracy, at the end you have 100 classes and you have a certain accuracy. Of course, the problem with 100 classes is going to be more difficult, even if the model didn't forget anything. An alternative measure can be this cumulative accuracy, where instead of using all the units, you just use the units that the model has seen when learning the task that you are evaluating on. So the future units are all masked. And I'm going to see you later that this makes a big difference. So there is another point that is important for stability. So if you observe, this is the curve of a real experiment for a single task, not for all the data. You can see that after a drift, what happens is that the model accuracy goes very low, and then it starts going up again. In some sense, the model is forgetting and then learning again. Of course, we want to avoid this. We would like the model to, the model accuracy to not drop at any point. This phenomenon is called the continual stability gap from this iClear paper from this year. And this is why I told you that it's important to measure the metric along the entire curve, because if you measure only at the task boundaries, you are not going to see the effect of this stability gap. So there are some metrics to measure the stability gap. Basically, they are going to look at the worst case accuracy along the curve. And the idea is that you don't want only the average accuracy or the final accuracy to be good, but you also want the worst case accuracy to be as high as possible. Okay, and finally, I told you about linear probing. So we also use linear probing to measure the quality of the representation, because if the classifier is misaligned, then maybe it's not that big of a problem. We know how to fix it. If we have a replay buffer, for example, we can just compute another linear classifier using the data from the replay buffer. And so these are the results on the metric that I've shown you. So the final accuracy, the average anytime accuracy, the worst case accuracy, and the linear probing on CIFAR100 and TinyImageNet for several methods in online continual learning. So the first thing that I want to point out is that different methods are optimal on different metrics, and this is true for both benchmarks. So if you look at the final accuracy, maybe the replay plus LWF is best. If you look at the anytime accuracy, SCR is best. So one thing that SCR is doing, for example, is changing the classifier. So the problem that I told you before about the misaligned classifier doesn't happen here. And maybe this is why the method has a best worst case accuracy compared to the other one. Another thing that you can see is that the linear probing is actually best for the naive experience replay. So this is experience replay with reservoir sampling. So it's a bit strange that we got the best result on the most basic methods, because you would expect the others to be much better. So in general, it's still an open problem, I think, online continual learning, because we have many different metrics that we care about, and most papers are going to focus on one of these two, but they are not going to be optimal on the other. Some other results. So here I'm showing the forgetting against, so the solid lines against the cumulative forgetting, the dotted lines. So you can see that when you exclude the future units, actually the forgetting is very small. Of course, this is not perfect because part of the forgetting is like you are not really separating completely what it means to forget and what it means to not forget with both methods. But again, it's interesting to see that a lot of the forgetting that we see with the standard measure may come from the fact that the task is just becoming harder. Here on the middle is a plot that is measuring the stability for SCR in orange and experience in play. So you can see that the orange curve is much smoother. After here, you have the drift. So when you get the new classes, you can see that there is no catastrophic forgetting like we had, like we have, for example, with experience replay. And the other plot is just the accuracy with different memory sizes. Okay, so this continual stability issue is a relatively new problem. So it's not clear how big of an issue it is in practice, especially because since the linear probing is actually good, maybe it's just a problem of the final layer or something that can be fixed very easily. One thing that we tried to do is to use temporal ensembles, so an exponential moving average of the weights. With this method, you have a separate training and evaluation model. So the training model is the normal one. The evaluation model is the EMA of the weights. You can see the results here in the plot. So solid lines using the training model for evaluation, dashed lines using the EMA for evaluation. You can see both that the accuracy is way better along the entire training curve, and also that you have smaller drops at task drift. There is still an open question on how to fix the stability gap during training. We tried to do simple things like distillation using this EMA model, but it didn't really work that well. So of course, this is also a CoLLAs paper. So if you want, you can check the poster, and Albin is here too. Finally, so for this section, I also want to mention the problem of hyperparameter selection. Most of the time, when you see a continual learning experiment, what happened is that someone did the entire stream, picked the best hyperparameters, and then they trained again the model with the best hyperparameters. At least two problems with this method. First, it's not a continual learning method, so you are looking at future data to pick the hyperparameter that you're going to use early. And second, it's not even optimal because, for example, if you have a parameter which is a regularization strength, you can easily expect it to change over time. Like maybe you need more regularization the more you train, or maybe you need less, whatever, but for sure, you don't expect it to stay constant. So there are some methods that try to fix this issue. Like the first one that I want to mention is use large batches. So the idea is to find the optimal stability plasticity trade-off. If you assume that there is a single hyperparameter that controls the plasticity, like the regularization strength, then you can do it just by looking at the accuracy of the current task. Basically, you have two two loops here. In the first one, you find the learning rate that gives you the maximum accuracy on the current task. And then in the second one, you increase the regularization strength as much as you can without dropping the accuracy too much. You have this threshold on how much you allow the accuracy to decrease. There are also other solutions, like based on online reinforcement learning methods, like bandits, or an alternative is to just take the first part of the stream, do the hyperparameter selection on that, and then train. Of course, if some hyperparameters may depend on the length of the stream, this is a problem because they are not going to generalize to longer streams. And I think this is another reason why we shouldn't do the hyperparameter selection on the entire stream, because then you don't see if a method is really exploiting the fixed length of the stream that is going to see during hyperparameter selection and training. An alternative that I think is more promising than doing continual hyperparameter selection is to just design robust models, so models where you either need less hyperparameter selection or where you can find somehow the hyperparameters automatically. For example, in this paper that we recently published, we found out that most continual meta-learning methods were quite unstable. This is not a big surprise, of course, but basically this method that we designed is using just a single inner update step, and by using a single inner update step can use exact gradient instead of first order approximations, and we ended up having a better accuracy overall. So I think in general, being more careful about how we do also the hyperparameter selection can lead to more robust models that then don't even need that much hyperparameter selection on the full stream. Okay, so finally, as I told you in the beginning, we may have real-time constraint, but another constraint that instead we often have, but it's not a real constraint, is the memory. So the truth is that memory is cheap. Usually it's the compute part that is expensive. And most methods in continual learning are designed for finite memory. And finite often means like very small, like few thousand examples. There is a privacy argument. So people say that you shouldn't keep the old data because of privacy, but it's not a very strong argument because, of course, the model itself can leak data. You can't just give a trained model and then say this is private. So in general, I think there is this still unsolved problem that is the real-time constraint on one end and the infinite memory, but with bounded computations, which is another problem. So some methods are continual learning methods, but are quite expensive to train in practice. So the idea when you have real-time constraint is that if your method is not fast enough, then you need to skip data. Like you can see here a coefficient, like experience replay, let's say has a coefficient of 1, and a strategy like GSS may have a coefficient of 6 because you need multiple forward and backward passes for each step. So basically, GSS is going to skip 5 samples. It's going to see 1 every 6 samples. There is this very nice paper at CVPR this year that did exactly this experimental setup. And the result is that experience replay, so the most naive thing that you can do, is outperforming all the continual learning methods that they tested when given the same computational budget. So this is quite unexpected, and I think it's possible to improve over it. But surprisingly, continual learning methods are not designed to solve this issue. Okay, so I think there are at least 4 questions that are unsolved right now in continual learning. I think many of them are easy to solve. So we just have to put some focus on it. The continuous stability issue, the robustness to stream hyperparameters, so being careful that methods are not just designed for class incremental learning, but more general and realistic streams. The problem of robustness to hyperparameter selection or real continual hyperparameter selection, and compute-bounded continual learning. Okay, so this now we start the third part. I want to talk to you about what happens when you have more than one continual learning model. So I'm going to briefly mention continual pre-training, so how continual learning fits in the training of large models, especially with what kind of evaluation I think is useful in this setup. And then I'm going to talk about what happens when you have instead completely independent continual learning models that want to share knowledge between them somehow. So in continual pre-training, you have the problem of efficiently updating a large pre-trained model. Here, let's make the example of language model. So you have, at first, you will have a very general model that you trained on some general domain like Wikipedia. And then you decided you want to focus on scientific papers. So you use the archive feed to update your model regularly. And so every week, you get a new model. Now you have to do two things. First, of course, you want to evaluate on downstream tasks because you want to see that the model is actually improving on the domain-specific task that you care about, like document classification of scientific papers. This is the easy part, of course. If it doesn't improve, it doesn't make sense to do this continual pre-training process. You just use the general model. But you also want to control if the model is forgetting some general knowledge, right? You start from a pre-trained model. You don't want to forget everything that the model learned during the first pre-training phase. So you need to have some kind of task, like sentiment analysis on tweets, that is completely independent from your domain, that you use to check the fact that the model is still general. Right? So what happens, and I mean, we have all other talks on continual learning at scale, so I'm sure that they will give you much more details than I can give you here. But basically, pre-trained models, large pre-trained models are very robust to continual learning. You can see that the accuracy basically didn't drop with this vocabulary expansion method. They are also very fast to learn, so you just do an epoch and you're done. And another thing that we found is that in general, self-supervised pre-training is much more robust than supervised methods. When we did some experiments in vision, we saw that the pre-trained model with supervised objectives in general forgot much more. So this is one of the reasons why people are starting to focus also on self-supervised continual learning. Here in the slide, I'm showing you two different methods. On the left is Castle, and on the right is the projected functional regularization. They are both from last year. The high-level idea is that you have a copy of the previous network and the current model, and you try. So the current network should be able to reconstruct the old representations of the old model. Of course, not exactly, but you use a predictor network to map the representation of the new model to the old model. So even if the representations have changed, the model didn't forget the old stuff. Of course, you use all the self-supervised learning tricks that you know from the standard self-supervised training literature. And this is another setting where the linear probing evaluation is really important, because when you have a self-supervised model, then it's the way in which you have to evaluate it. Now, instead, I want to talk about the setup where you have more than one model. So instead of having a large model, let's say that we have many different local models. And the usual way to solve this is to do federated learning. So each device has its own local copy of the model. Then every now and then they synchronize with a server, share the data, aggregate the weights, and then the server is going to send the updated weights, right? The problem is that federated learning methods fail in these very simple heterogeneous settings. You can check this paper for some results. So there is this phenomenon of local forgetting. Basically, in an heterogeneous setup, so either the data in each local device is very different, or maybe you don't aggregate frequently enough. Maybe there is some client that doesn't send the model quickly enough. What happens is that there is a local drift, so the local model is going to be very different from the central one, and the aggregation is not going to work anymore. So there is the question of, can we use continual learning to improve federated learning in an heterogeneous setting? Like this paper that I used is proposing this weighted cross-entropy loss to mitigate this problem. I'm not going into detail about it, but this is also a CoLLAs paper. It's not my paper, but check it too. Another method on also for continual federated learning is fed-weight. So fed-weight is based on the idea of minimizing the communication. It's a task incremental method, so it uses task labels. And the idea is that you have a different model for each task. So you want to exploit task similarity while avoiding task interference, like the masking-based methods do in task incremental learning. So basically, what you end up with is a local model that has 3 types of parameters. The global parameters are the ones shared by all the local clients. The local-based parameters, these are the client-specific parameters. And then you have some task-adaptive parameters. So for each task, you have a small number of parameters. And this is how the model looks like. So you can see that the global parameters are masked so that there is no interference and very few parameters are used for each client. And also the task adaptive parameters can be shared by learning this weighted sum of the parameters. Since everything is masked, there is actually very little data to send around. So it's quite effective. But now I want to change the setup a little bit. So I think, in general, the problem with the continual federated learning is just in the operation of aggregating the models together, right? Because we already know how to train the local model. We just do continual learning. And we already know how to aggregate homogeneous model. You just average the parameters. But to aggregate the model, you need to assume that the aggregation is frequent enough so that the local models are all homogeneous and this aggregation actually works, right? So this begs the question of, like, can we actually do the aggregation of models that are very different with each other? We tried to study this scenario. So with this sequential model aggregation, we called it X model continual learning. The idea is that it's, again, sequential. So you don't, it's a continual learning problem. But instead of learning from the data, you have models. Each model learned a single task. And then you learn how to do the aggregation so that this continual learning model in the end is like the aggregation of all the task experts, right? Now, this is still largely an unsolved problem, let's say. But if you can solve it, then you can free federated learning from the requirement of very frequent synchronization. So you can allow decentralized learning where each model is learned completely independently, and then at some point it's aggregated together. So it's related to what is called also model patching. The idea of model patching comes more from large pre-trained models. The idea is that you can imagine divergent models that are specialized on different domains, are different branches of the history of the model. Think about like a Git history. So at some point you want to merge them, and how to merge them is the model patching problem. So we also try to solve this model aggregation issue with a method that we call data agnostic consolidation. The idea is that once you have this operation of model aggregation, you can split learning into two parts. First, you have the adaptation, where you learn a new task, and then you have the consolidation, where you aggregate the models, right? And if these operations are completely independent, you can also do them on different devices, like you do in federated learning. This method that we proposed is based on data-free knowledge distillation. So it's going to use some kind of out-of-distribution data to extract augmented samples. And then it does knowledge distillation for each head. It's a task incremental method, so a different head for each task. And also in the latent layers by projecting the latent activations in a different space. Now, the most interesting result that we got from this paper, I think, is the fact that when we tested this approach based on adaptation and consolidation, the result on standard task incremental benchmark were better than the popular task incremental baselines. So I think, in general, having if you have a task incremental problem, for example, or even a class incremental problem where you have these sharp boundaries, it may be useful to have an operation like a model consolidation at the sharp boundaries, where you are somehow able to fix possibly the forgetting that may happen during the adaptation step. So this consolidation different models, I think, is useful even outside of this setup, right? So there is other work in this area, like one paper that I like a lot is called batch model consolidation. It's a very recent paper. And in their case, instead of having just one single model for the aggregation, they have K models, and then that are trained completely independently again, and at some point are going to be consolidated. And so during the adaptation, they have a regularized adaptation phase. So basically, instead of just training on the new task, they do distillation of the base model. Like this is the base model is used like a teacher, so that the task expert don't diverge too much. And then during the consolidation, they use a small batch of replay data to help consolidate the model. Again, this allows you to do sparse consolidation between the models. So it's actually possible to learn all these K tasks in parallel, for example, and then when necessary, consolidate them together. Okay, so let me draw some final conclusion for the tutorial. So in general, the goal of continual learning is to understand how to design machine learning models that learn over time on a constrained budget. So maybe it's memory, compute, real time, whatever. If you remove these constraints, you can actually just train from scratch every time. So it doesn't really make sense to even talk about continual learning. And you have non-stationary data, right? So the goal is much wider than doing class incremental learning, or I don't know, taking a pre-trained model and fine-tuning it for 5 steps, right? It's really a question that makes sense only when you think about the constraints and when you think about the scale, like long time scales, even if, of course, your experiments are going to be small, possibly, and this is fine, but you have to think about whether your small experiment then generalize to longer time scale, right? So toy data is fine, I think, but the toy setting are not so fine because it's very easy to find a shortcut to either avoid continual learning or I don't know, make it very easy. Same goes for the metrics. It's very easy. Like there are a lot of metrics in the continual learning community that are very easy to abuse and to use it for misleading readers. But the good news is that like there is a lot of work that is trying to either devise more realistic benchmarks or better metrics and whatever. So you don't have to invent everything from scratch. There is a lot of space for improvement. So I'm going to leave these open challenges. Basically, these are the things that I try to highlight in the tutorial and that I think are easy to solve. Most, maybe not all of them, but some of these I think are easy to solve. We don't have really many solutions, so even a small improvement is enough. And they are quite important continual learning properties. So for the benchmarks, they making methods that work on real drift and frequential evaluation, the exploitation of temporal coherence, the real-time training with infinite memory, robustness to stream parameters, hyperparameter selection, stability gap, and finally, the going beyond single agents, so continual pre-training and the idea of continual learning. Okay, so I just want to let you know a bit of advertisement. We have this library based on PyTorch for continual learning. It's called Avalanche. It's a community effort from the ContinualAI community. We have lots of continual learning methods. It's a lot of different contributions. And so if you are interested in using it, we have this project. We have the baseline reproducing papers. This is the class-incremental with repetition paper that I showed you in the slides. And this is the online continual learning survey that I showed you in the slide too. Okay, so this is it. Thank you.
You mentioned that experience replay does really well. I just was wondering, what are your views on pseudo replay or generative replay? Second question is, could you mention or what do you think about mechanisms for gracefully forgetting, because we do not have them?
Okay, so for the latent replay and generative replay, I think a lot of the effort came from the idea that methods should be replay free. And I don't really agree with the view that methods should be replay free. I don't think I mean, it's an interesting objective from a neuroscientific perspective. Like Vincenzo said, there is this idea that the brain doesn't really replay raw images, but latent representations. So it makes sense. And possibly there is a way to make it work. Right now, I don't think the results on latent replay are competitive with raw replay. But so I think it's for practical applications, it's always better to have raw images, but it's an interesting, let's say, more theoretical question. And then the other question was the forgetting. So I think in general, you will expect methods to forget naturally if you don't do anything about it. Like in a scenario with real drift, I don't know, if you have, you're classifying cats and dogs, and then at some point you change the labels, then the model is going to learn to change the labels. I don't know. Or so I think it happens naturally, and you don't need to do anything about it. There is the question, like if you really want to forget something and enforce forgetting, I don't know. I'm not familiar with that line of work, so I can say.
I have a question. I might not the answer, but before testing. So for sequential evaluation, what are, do you happen to know what are the assumptions behind it, and do we know if those assumptions actually hold? Because always in this kind of evaluations, there is some theory, like for example, even the normal ID, right? There is some theory, and then there is what to do in practice, and it's not always clear if those things match. And like I don't know, like if you have any knowledge about sequential evaluation comes from and what it assumes.
Yeah. So usually the frequential evaluation comes from the forecasting community, I think, right? So there it makes a lot of sense because you're predicting the next time step, and then you're going to see it, and you train, like it's like you're training your model to correct its predictions based on what the actual world is telling you. So it's, in some sense, it's the natural way to train and evaluate a model in the forecasting world, I think. But I talk about it in the context of image classification. So there it's very different. Problems that you can have, like you're not going to have the labels. So of course, there is this assumption that someone is going to give you labels, but you have to give them. And then there is the assumption that the labels will come as soon as, like soon after you have a prediction. This is also not true. So there is going to be some delay, like right between when you make the prediction and when you actually get the labels.
Thank you for the talk. So my question is, I love continual learning. One of the things that often frustrates me is both you and your colleague cover this. There's this huge focus on these very, what I feel like are contrived settings. For example, the class something.
Class-Incremental.
Then there's also the task something setting. A big focus on these. Do you think it's because these are the problems that people actually care about, or is it about like these are the benchmarks that people have developed and where people often test things? Or is it because perhaps we just don't have methods to tackle like these more realistic, very difficult settings?
Yeah. Okay, so I have to be honest here. I think the focus on class incremental learning is just due to how we review papers, like how the community is organized. So basically, working on class incremental learning is a very easy way to say that you are doing continual learning, and then like you show a lot of forgetting, so people know that it's different from normal setups. Instead, when you work on, like, one thing that may happen with real drifts is that maybe you don't have as much forgetting. So maybe the naive baseline is good enough. You get a small improvement, but it's not as big as you get from class incremental. Yeah, so I don't think there is any good reason. Actually, one of my hopes is that like a specialized conference like CoLLAs can fix this limited view of continual learning, because maybe like reviewers are more specialized and they can appreciate more like more general work.
the models are growing bigger and bigger. So in that way, like the paper, most of the paper claims like they are eliminating, targeting by growing the model size because there's a lot of parameters to hold this knowledge. So what's the general take on it? So another question to a topic of this, like it's like kind of a balancing problem, right? Like for example, if new task comes in, the model has to balance the previous task and the current task. So what if there's like some external memory for which the model can use? So what's your general opinion on this?
Okay, so first, for the first question, we have some results that show that wider models forget less, and the wider you make it, the less it forgets. So it's true. Like, it's something that we know empirically. There are good theoretical reasons. It's just a matter of how much resources you have. So basically, the best thing that you can do is to make the model as big as you can. This is a question that we know how to answer. The second one, I'm not sure.
Like using a smaller model but having some kind of external memory, so that it doesn't forget some previous task or something.
What kind of external memory?
Like using some adapters, growing the network.
Oh, okay. So there are methods that are the task incremental methods, especially may have some modular network. Like you have for each task, you have some task-specific parameters, like here in weight. So basically, this is the definition of the models, but not all the models are going, or not all the parameters are going to be updated when you train on a new task, right? I think this is what you were asking, right? Mm-hmm. Yeah, exactly. And then the adapters tell you how to use the models for the parameters for all the tasks. So this here, like AI, are the parameters of some task, and alpha I will be the adapter in some sense. It's not really an adapter. Here you are summing the parameters, but you get the idea.